minimal constructions in the sharply minimal setting. Please begin.
Okay, so thank you very much for inviting me. This will be a continuation of Gal's talk, where we talk a little bit more specifically about sharply or minimal structures, but we will mostly talk about an effective and cylindrical Yomdin-Gromov algebraic lemma, so not algebraic. All right, so I'll just remind you of the axioms. So we say that sharply or minimal structures is when we have the format degree filtration on the definable subsets. And kind of we have the first axiom, which controls connected components of subsets of the line. So it has polynomial components in the degree. Also, all of these first order logic operations, then they will not change the degree, but increase the format by 1. A small technical axiom is that if you have a set in RL, it can't have a format that's very small. It must have format at least L. Okay, another first order logic axiom is about the union and the intersection, that they increase the format by 1, at least intersection, and the degrees add up. And here the size of the union is arbitrary. Okay, so a polynomial hypersurface has a format equal to the amount of variable and degree equal to the degree of the polynomial. And another axiom which does follow from the other ones, but maybe with not format 2 and degree 1, but still so that the list of axioms will look very similar to the list of minimal axioms. The subset x equals to y, x smaller than y has a format 2 and degree 1. Okay, and just some notation. The capital letter I will mean the open interval between 0 to 1, and pi m will mean the projection on the first m coordinates. So usually n will be omitted. Also, we can speak of format and degree of definable functions. So definable function has format f and degree d if its graph has these formats and degree. And for the entire talk, we will fix an integer r, which will correspond to the order of smoothness of our operations. So let's begin with kind of a very easy statement, just to warm up to see the mechanism of the axioms. So suppose f is a definable mapping from IL to IS, and it has format and degree d. Then f is CR smooth outside the definable set of codimension 1 of format OFR of 1 and degree polyFR of d, and the number of coordinate functions S. So it follows from all minimality that the set V would have codimension 1 or more, but why can we bound its format and degree? Well, the idea is that we can write this condition with a first order formula. Okay, so let's look at the set AI, the set where the ith coordinate function is differentiable. And we can give it by the formula just equals, okay, not equals, sorry, exists Li, and Li is the basically the differential of Fi, so it is a vector with L elements, and then these standard things where Fi can be approximated by a linear functional. So we prove it for R equals 1, but a very similar proof will work for a general R. And just as Chris Miller said on Monday, so these axioms of minimality or sharp minimality are just about parsing first order formulas. So what it means that the set AI can be described by taking complements and projecting OFR of 1 times the set BI, which is given by the same formula just without any quantifiers. And now by the axioms of sharp or minimality about arithmetic operations. So plus is an algebraic operation, and we will see that the set BI has a format OFR of 1 and degree polyFR of D. So BI has it, therefore AI has it by the axioms, and therefore the intersection also has it. And okay, by minimality, we know that if we remove the intersection from the cube, then F will be a CR smooth. And I just want to kind of say that why don't we write like a very long formula, exists L1, exists L2, exists L3? Why do we really need to think about it as the intersection of AIs? Is because in this long formula, you'd have S variables. And then S would enter the format of this equation, of this formula rather. And we know that that's something we wish to avoid.
I'm really sorry. Can you hear me now?
Yes.
Yeah. Okay. So I have
You're clear.
with my headphones. All right. So if we try to work directly, then we'd have S entering the format. So format is not exactly a length of a first order formula. It's more like the depth of the parse tree. And also not exactly, because we allow arbitrary size intersections, but still. Okay, so this is just the mechanism of the axioms. It's very typical that we borrow the result from O minimality and just say, okay, we can define it with such and such formulas. So we will have good bounds on format and degree. Some other results which are a little bit harder or more involved is just stratification, for example. So if a set is definable and has format F in degree D, then you can stratify it into poly FRD CR smooth submanifolds of RL. And each manifold, each piece will have, each strata will have a format OFR of 1 and degree poly FR of D. So this you can prove very similarly to the statement before, just the formulas will be longer. And the result, which is slightly more involved, is that if X has format F and degree D, then you can bound the amount of connected components it has. So poly FD connected components. You can't bound the format and degree, or at least we don't know if you can, of its connected components, but you can bound the amount of connected components. So now that we've got this out of the way, let's talk about Yomdin-Gromov algebraic lemma. All right, so just a small definition. If we have a function from a domain U, a function of a single variable, which is between 0 and 1, the function itself, then we denote just this usual notation for the supremum norm, and we add a subindex R to mean the maximum of all of the norms of the derivatives up to order R, normalized by the factorial of the order of the derivative. Okay, this is for a function, and for a map, we can just say that its R norm is the maximum among the R norms of its coordinates. And we will just say that if a map has R norm smaller than 1, we will call it an R map or R function, respectively. Okay, so what is the Yomdin-Gromov algebraic lemma? So the theorem is that if X in IL is a mu-dimensional semi-algebraic set of complexity beta, so by complexity here, I mean just take some presentation of X as a union of systems of equations and inequalities, and beta will be the sum of the degrees of the polynomials involved. Okay, then there exists a constant, which is polynomial in the complexity n in R, and so many maps, F1, F2, Fc, are maps which cover your set. And okay, for those of you that may see this for the first time, it's actually quite a strong result, and maybe just an elementary consequence for us is a bound on volume, just to ground this result and think about how powerful it is. So a volume of a pure dimensional semi-algebraic set of complexity beta is polynomial in the complexity. It follows immediately from this theorem. All right, and one more remark about this theorem is that, at least for the semi-algebraic structure, which has a very analytic nature, you might ask, what if we want the parametrizing maps to be analytic? Like, why do we need the CR smoothness for a finite R? Well, in fact, you can't. You can't do it uniformly over beta. And there is a very nice reason, but which I don't have time to tell, unfortunately. But it's just untrue for analytic parametrizations. And I will mention that we don't just parameterize the set. The Yomdin-Gromov lemma is about controlled parametrizations. So the parametrizing maps will have a derivative smaller than 1. So for analytic maps, how would you control an analytic map? You would say that it is defined on a large domain and its norm is smaller than 1. So that would be enough. So for example, the concept of an R map will be replaced in the setting by a map defined on a polydisk of radius 2, which is bounded on 1 on the polydisk of radius 1, something like this. Okay, so this is just a remark that really it's about CR smoothness. And in their paper, Pila and Wilkie, where they proved the famous counting theorem, they needed this Yomdin-Gromov lemma for general or minimal structures. But generally, there is no notion of complexity, and the effectivity of the Yomdin-Gromov lemma on beta is replaced just by uniformity over families. So this is the theorem. So we have XP, a definable family of sets of dimension at most mu. Then there exists some constant depending on the total space and on R, and such that for each parameter P, there are definable R maps that whose images cover XP. And I will mention something now that will also be relevant later, that this Pila-Wilke version does not prove the theorem I said before, because you might want to apply it to the family of all semi-algebraic sets of complexity beta or smaller than beta. Then indeed you will get a uniform bound on the amount of maps depending on beta, but it won't be polynomial. So in the semi-algebraic case, you really have something more. Okay, so what about? Yeah. I think it's Waldo, right? Okay, I'll continue. So what about effectivity beyond the semi-algebraic situation? So actually, it was already explored in the sub-Pfaffian structure. So there is an effective version, both of the Yomdin-Gromov lemma and of the Pila-Wilke counting theorem for sub-Pfaffian surfaces. So this is due to Jones and Thomas. And also there is a work in progress by Bignamini, Jones, Schmidt, and Thomas, as Gal mentioned earlier, to make an effective version of the Yomdin-Gromov lemma in general. I mean, for not only for sub-Pfaffian surfaces, for general sub-Pfaffian sets. Okay, so what will we be talking about? We will be talking about, first of all, making it effective in the sharply or minimal setting. But moreover, notice that in these two formulations and in the next formulation I will give, there is no connection between the different parameterizing maps. So there is no combinatorial structures, and their images do not decompose the set X. So what I propose is, first of all, an effective version for the sharply or minimal case, but also a version which has very strict combinatorial restrictions on the parameterizing maps. So for this, I will need to first of all talk about the cellular version. So for this, we need the concept of a cellular map. So a cellular map between two definable subsets with definable sets with the same number of variables is triangular map, which means that the ith coordinate function depends only on x1 and on xi. And secondly, that it is strictly monotone and increasing on fibers. So for every fixed x1 up to xi minus 1, the ith coordinate function is now a function of one variable, and it will be a strictly monotone increasing function of this variable. And this is a precellular map. We need this for some reason, but usually the concept is a cellular map, which is a continuous precellular map. So the way the cellular maps works, that they begin with something like a square, and their image is always a no minimal cell. So you can take that as a definition of a minimal cell if you haven't heard of it. And so the first coordinate of this map will parameterize x1, and for every fixed x1, here we have phi of x1, phi1 of x1 rather, and then the second coordinate of the map will map this straight line onto this line smoothly and monotonically. So just to imagine how cellular maps work, and in particular, if we fix some of the first coordinates, then the resulting map will also be cellular from the appropriate domain. So this is what we write here in this remark, just that if you fix any for I tuple of first coordinates, then the resulting map will also be cellular. And also we need the concept of a basic cell, because cells, minimality, they have different types. They can be vertical in some variables and horizontal in others. So the natural domain for a cellular map is what we call a basic cell. It's just a product of L either points, just 0, or intervals I. And then the image of a basic cell will be a no minimal cell of the same corresponding type. Okay, so the following is a cellular version of the Omdi-Gromov lemma for O-minimal structures, and it is due to Benyamini and Novikov. So it has a set version and a function version. So the set version is that for every definable set X, there exists a finite collection of basic cells. So basically, you cover X by O-minimal cells, and then each one of these O-minimal cells you parameterize by a cellular R map. And there's also a function version, which is what you might expect. You have the set X, and on it you have a function with Q coordinate functions. So also you can parameterize X by R cellular maps, such that the pullback of the function f on X is also an R map. So notice that by the remark I gave before, that automatically, unlike normal Omdi-Gromov lemma formulation, because of this cellular feature, this formulation is automatically uniform over families. So if you have a family, just find a cellular parameterization of its total space and then fix a single parameter, you will get a cellular parameterization of the fiber. All right, so how would we make this result effective? And this is already something that Benyamini, Jones, Schmidt, and Thomas do. But it also has connection about the combinatorics that I'm going to be talking about soon. So what are the problems of effectivity here? So the first problem is that the coordinate functions of f are parameterized one by one. So you can imagine you have q scalar functions, and you want to parameterize them. And say to parameterize one scalar function, you need n pieces. So what you could do, you could parameterize one of them. So you get n pieces. And then on each piece, you parameterize the second one. And then on each piece, you parameterize the third one. So if you do this, you'll end up with n to the power q pieces. So exponential in q, and it's problematic. And also, there is some kind of logic compactness argument, which they use. They say that if you know FL, you automatically know FL for families. But for a reason similar to what I said before, that the family of all semi-algebraic sets of complexity beta has dimension which depends on beta, this argument will not work in the effective case. All right, and these two things are just about effectivity, but they have a lot to do with some combinatorics. So how do we fix this? So for the first thing, instead of parameterizing the functions one by one, we show that actually we can parameterize them all at once with an effective number of pieces. So this is just a refinement of Gromov's original argument from the paper Entropy, Homology, and Semi-Algebraic Geometry. And the second one, which is more similar to what's going on with Benyamini, Jones, Schmidt, and Thomas, is that instead of kind of trying to do a compactness argument, we just work throughout with parameters and keep track of the format and degrees of the total spaces. So this is the plan. And now I will tell you what I mean by finding a parametrization which has combinatorial structure. So here, it already has some structure because the pieces are cellular and the pieces are cells and the maps are cellular. But still, all the different pieces, they only cover X, they do not decompose it, and there is no connection between different cells. All right. So what is a cylindrical decomposition as opposed to cellular decomposition? A cylindrical decomposition, it's a cellular decomposition with an inductive structure. So in dimension one, it's the same thing, but a cylindrical decomposition of a set in dimension L is just some kind of cellular decomposition of it, such that there exists a cylindrical decomposition of the base, such that the cells of the original decomposition are, if you project them down, you get cells from the base. So in particular, the projections of cells of cylindrical decompositions are always either the same or disjoint. So on the left-hand side, we see a cellular decomposition of the square, but it's not cylindrical. So these two cells, for example, this one and this one, their projections onto the first axis, they intersect, but they're not the same. But on the right-hand side, we fix it and we refine it into a cylindrical decomposition. And here you see that there is a cylindrical decomposition of the line. And for every cell, there is a decomposition of the cube over the cell with cells that project surjectively onto the cell in the base. So this cylindrical decomposition has an inductive structure, unlike general cellular decompositions. All right, and so I'll talk a little bit about reduction of the filtration. So Ari asked Gal, and Gal already said something about it. So, but if we have a sharply minimal structure, so here S is just an minimal expansion of the real field, and omega is the format degree filtration, we can define the filtration omega star. So how would it work? And the thing is that you can't really define connected components in no minimality. So it's a non-trivial fact that a connected component of a definable set is itself definable. It follows from cellular decomposition. And similarly, we just don't know how would we bound the format degree of a connected component of a set of some format degree. So we kind of force this. And of course, we have to pay, but the price is not too high. So what's going on here? So say X is a union of connected components of some sets. So X circ alpha is a connected component of X alpha, which has a format F alpha and degree D alpha. So if X has such a presentation, we say that it has star format F, which is the maximum among the formats of X alpha, and star format D, which is the sum of D alpha. So, okay, now we fix the issue with connected components, but it's not clear that this new filtration is a sharply or minimal filtration. But it turns out that it is. And this is why we have the effective cylindrical, on vice versa. We can prove an effective cylindrical decomposition theorem for this star format and star degree. And then from it, it follows that star format and star degree respect operations such as complements and projections. So the theorem, it's in preparation, but it's mostly proven. So if we have S subsets of IL of star format F and star degree D, then there exists a cylindrical decomposition compatible with them. So compatible, I mean, for every cell and every I, the cell is either contained in Xi or disjoint from it. So the amount of cells will be polynomial in the degree and the amount of sets we started out with. And the star format of the cells is OF of 1, and the star degree of the cells is poly FD. All right, so now we have, in the sharply minimal setting, we have the basic tool of minimality, an effective cylindrical decomposition. And now we think about, finally, I get to say something about what do I mean with all these combinatorics. Okay, so this is the notion of a cylindrical parametrization. So what is a cylindrical parametrization? So suppose we have a cylindrical decomposition, C alpha, into cell C alpha of some set X. For us, X will just be the cube. What is a cylindrical parametrization? It's, okay, so every one of the cells will be parameterized by a cellular map. But we want that if the cells are on top of each other, in some sense, so if their projection onto some coordinates is the same, then that part of the cellular of the parameterizing maps will be the same. So if for any two cells, C alpha and C gamma, we see that if we project them down onto the first K coordinates, we will get the same cell, then also the first K coordinates of the parametrizing maps are the same. And okay, we will call this cylindrical, excuse me, this, okay. Pressed, right. So, okay, we will call this cylindrical parametrization, and our parametrization if all the cells are R maps. So I promised you that this combinatorics have something to do with parametrizing the functions all together. So say you have a set, or maybe a set which is just a union of a few graphs of functions of one variable, and say the graphs don't intersect so that they already form their own cylindrical decomposition. So to say that you want, so all of this is just a cylindrical decomposition of I squared, say, and if you want to form a cylindrical parametrization of it, what it means is to find the function that, you know, it parametrizes X somehow, but then because all of these functions are on top of each other, these graphs, we want the Y coordinate to be basically parameterized by the same parametrization of X. So we have these functions. So finding a cylindrical parametrization for these graphs is the same as finding a parametrization of the x-axis, which makes all of these graphs are maps at once, are functions at once. So there is the connection. And also there is a very nice way to visualize cylindrical parametrizations. So on the right-hand side here, we have some cylindrical decomposition of the square. So we have, over this cell, we have 5 cells, 1, 2, 3, 4, 5. Over this cell of lower dimension, we have just 1 cell. Again, 5 cells. Here, over this point, we will have 2 cells. This is the first one, and this is the second one. Here we have 3 cells, 1 cell, and again, 3 cells. So we define a fort. So basically, a fort is we take the domains of the parametrizing maps and we put them together in space so that all of these parametrizing maps phi alpha, or all these cellular maps, they fit together to create a single precellular map. So on the one hand, the fort is a completely combinatorial object, discrete object. So all of these cells, they have side length either 0 or 1. So it's the moduli space of forts is completely discrete. But on the other hand, all of these functions really glue to a single precellular function. And it is not continuous. It is not continuous because, well, so for example, a point here will be mapped somewhere around here. Let's do it the other way around, sorry. So a point here on the second cell will be mapped to somewhere around here on the second cell of this guy. And a point nearby will be mapped to a point here. So it's not continuous along x1, but it's continuous on fibers. And actually, all our main results are formulated in terms of forts, and they are uniquely suited to work with the cylindrical parametrizations. And okay, so now we can finally state our main result. Okay, so first of all, just the refinement. Cylindrical decomposition phi prime is a refinement of phi if each cell of phi prime is contained in a cell of phi. So we want to find an R parametrization for some cylindrical decomposition. And of course, we can't do it. We can only hope to find an R parametrization of some refinement, because the cells of the original decomposition may be very bad, for example, have a large length. Okay, so we also have a set version and a function version, but the function version is just there for induction purposes. After you have this, then you can just apply the set version to the graphs. So I will only state the set version. So suppose you have phi, a cylindrical decomposition of the cube into n cells of star format F and star degree D, then there exists a refinement of this decomposition with size poly dn. So n would be the, okay, so depending on the degree of the cells and on the amount of the cells. And phi prime already admits a cylindrical R parametrization whose maps have a suitable R format and R degree. Okay, and I want to mention that in particular, so how do we, first of all, how would we use it to find the cylindrical parametrization of a general set X? We just take a cylindrical decomposition of the cube that is compatible with X and parameterize it. So instead of parametrizing a single set X or some collection of sets, we parameterize an entire cylindrical decomposition of the cube, and it's a generalization. And the other thing I want to say that, sure, it's an effective version in the sharply minimal case, but it also has some content in the general minimal case. So even if we didn't start with sharply minimal structures, we could just remove everything about formats and degrees here, and still there would be some content because the maps have combinatorial structures. All right. So I will mention a little bit more about, so now that we have an effective Yomdin-Gromov lemma, we can hope to prove an effective Pila-Wilke lemma, just as Gal talked about it. And so we know a bound of the amount of connected components of a set of format F and degree D, which means that if it has format F and degree D, then it has star format F and star degree poly FD, which means that when we want to produce a finite set, so we start off with a set of format f degree d, then we look at its star format and star degree, do all these sharply minimal operations, and then we want to count something, we will still get bounds that are polynomial in the original degree. So this is why in the effective Pila-Wilkie, which is proved from this effective Yom-de-Gromov just in the same way as Bignamini, Jones, Schmidt, and Thomas prove it in the restricted subpfaffian case. So if A is a definable set, the amount of points of which are on the transcendental part of it and of bounded height are smaller than a polynomial in the degree, polynomial that depends on the format and on epsilon, times h to the power epsilon for every epsilon. So notice that although we pass to star format and star degree, this nice comparison means that we can still bound it using the original formats and degrees. So it's not such a high price to pay to pass to star format and star degree. And I will also mention that if we'd want to make it polylog, so Gal mentions that it's a conjecture that in a sharply minimal structure, we'll have a polylog bound here. If the problem is that all of our operations are exponential in R. R, the amount of the order of smoothness we want, because then basically it all boils down to the first proposition I showed you, where if you just naively try to look what formula makes a function a CR function, you'd have at least R variables, and R enters the format. And this is kind of the problem with making it polylog in general, but very possible that we can somehow avoid it, so that sharp structures are good enough that actually we don't really need R to enter the format. Okay, and I should have like a few minutes left, so I would like to discuss the main idea of this proof. So the main idea, again, is that we have this induction and we have some parametrization of the base. And so in the usual induction, you get a cell over the base and you parameterize it. And here, to achieve cylindricity, we need to parameterize all of the cells above it at once. So, and also this is a nice opportunity to get to know the very nice Gromov's argument. Okay, so suppose we have one definable function, which already has a bound on its first r-1 derivatives, where r is at least 2. So it's at least the first derivative is smaller than 1. Okay, so by minimality, we decompose I into intervals such that on each interval, the rth derivative is monotone and either positive or negative. And then we can use very nicely Lagrange's theorem to bound the rth derivative of x. So we look at this fraction. Of course, it equals to the rth derivative at some point between x and 0. And because the rth derivative is monotone decreasing, we see that it's larger than fr of x. Suppose the rth derivative is positive. And on the other hand, the first r-1 derivatives are bounded, so it's bounded by 2 over x. And this bound on the rth derivative, actually, you look at it and it does not depend on the function f. All you need is that f has bounded r-1 derivatives and that the rth derivative is monotone. And once you see this bound, the idea is to reparameterize the interval by x squared. So what happens when we do it? If we differentiate f of x squared r times, we get a bunch of terms where you only have derivatives of f up to order r-1. And all of them will just be bounded. And the only potentially unbounded term is the one where the rth derivative appears, but then the first derivative of x squared will appear to the power r. So it's something like 2 to the power r, x to the power r, the rth derivative of x squared, of f on x squared. And okay, so we know that the rth derivative of f on x squared is smaller than 2 over x squared. So overall, this term is smaller than x to the power r-2. But r is at least 2, so it's bounded. So this is how you deal with this situation. And you still need to achieve this initial data when r is larger than 2. So you want to make the first derivative smaller than 1. So this is easy. You have a function, so decompose the interval into intervals so that on each interval f is C1 monotone, and its derivative is either smaller than 1 or bigger than 1. So if it's smaller than 1, we are done. And if it's bigger than 1, we can parameterize by the inverse function. So if f would be monotone increasing, then the inverse function is also monotone increasing, and it is cellular parametrization. And if it's monotone decreasing, then we need to reverse the order of the interval first and then apply f to the power -1, and it would be monotone increasing. So this is how you do it for one function. But say we want to parameterize s functions at once. So I already mentioned that if we do it by one, we will have an exponential in s inside the amount of pieces we need. So how do we do it effectively with respect to s? So again, suppose they are all r-1 functions, and decompose I into intervals such that every one of these functions is CR and its arc derivative is monotone and has constant sign. And this kind of operation is not exponential because, okay, f1 is CR outside n points. f2 is CR outside n points. And so all of the f1 up to fs will be CR outside all of these points, which is just n s points. So this is not exponential in s. All right. Now, we can't just assume that FIR is decreasing because some of these guys may be decreasing and some of them may be increasing, and we can't change that. Okay, so if it is decreasing, just as before, we bound it by 1/x. And if it is increasing, we bound it just by 1/1 minus x. So we use the same argument as before, just with the points 1 and x instead of x and 0. And now we need to parameterize by a function which is not x squared, not 1 minus x squared, but a little bit of both. So it's this function whose derivative has x in it and 1 minus x in it. And now when we parameterize by this function, which is monotone increasing, so it's cellular, fi of phi, the arc derivative of it, is now bounded regardless of whether fi to the power r is decreasing or increasing. So some of them may be decreasing, some of them may be increasing, but we can fix both situations at once. All right. And okay, I should mention that we parameterized, we achieved the situation where the derivatives are smaller than a constant depending on r. Then we just, once we do this, we can just linearly subdivide our interval into n parts. And if we do it, then the derivatives will decrease by 1/n. So it's enough to bound the derivatives by OR of 1. And to achieve one functions, we do something similar to what we did before. We decompose I such that on every interval, we can, the derivatives of the functions are increasing. So f1 prime is smaller than f2 prime, so on, smaller than fs prime. And then it's kind of the same thing. If fs prime is smaller than 1, then all of the derivatives are smaller than 1. So all of these functions are 1 functions. And if the biggest derivative is always larger than 1, sorry, I should say that we need to decompose I into intervals such that this hold, that's what I wrote, fine. And such that fs prime is either smaller than 1 or bigger than 1. And in the latter case, we can parameterize by fs to the power -1. And because f1 and so on, all of the other guys have smaller derivatives, then after this parametrization, they will become one function. So their first derivative will be bounded by 1. And this is kind of the general technique to how we do things. We need to do a little bit more than the general technique so that we can parameterize a bunch of cells at once instead of one at a time. Okay, so this is all I had to speak about today. So thank you very much for listening.
Thank you very much. Again, is that anyone have any questions?